Welcome back to the Mechanics of Solid lecture series. This is part 3 of a series of videos on torsional stress and rotation examples. And in this video I'd like to quickly finish up the example we were working on in the last video. We solved part A for the maximum shear stress in the compound shaft. We summarize here the diameters of each of these internal shafts as well as the polar moment of inertia, which was found to do part A, and the internal torque diagram. In order to solve for the rotation angle, we need to know the relative rotations of each of these shafts with respect to each other. So we can add up and find the total rotation angle as the sum of the rotation angles in each shaft, which is found by summing up T sub I, L sub I over G times J sub I. And I left G without the subscript because G is the same for every segment. So notice that I can pull out a 1 over G and write this as sum over I T sub I L sub I over J sub I. So this is what we're trying to find. The units that we expect our rotation to be basically unitless or in radians. So we'll check that at the end. We know most of the numbers we need to go into this equation, but the units are tricky, so I'm going to be deliberate about this. Working units, newtons, millimeters, and megapascals. So we have several conversion factors that we need to consider. The first is that torque should be converted from a newton meter to a newton millimeter. 1 newton meter is 1,000 newton millimeters. Our length should be converted from meters to millimeters, so 1 meter is 1,000 millimeters. And finally, our shear modulus G should be converted from gigapascals to megapascal, noting that 1 gigapascal is 1,000 megapascals. Okay, so let's go ahead and plug in the numbers that we need. The total rotation angle is equal to 1 over G, G being 80 gigapascals or 80,000 megapascals, times T1 L1 over J1. T1 we'll use 1200 times 10 to the third newton millimeters. L1 being 0.7 meters or 700 millimeters, and J1 being 613,000 millimeters to the fourth. To save a little bit of time, I won't write out all the units for the other terms because they're the same. So we go on to T2, negative 3,300, 1,000 with the conversion factor, times L2, 1,800 millimeters, divided by J2, 4,021,000 millimeters to the fourth. And finally, add in for the third segment, T3 L3 over J3. This is also negative because the internal torque is negative. 500,000 newton millimeters times 700 millimeters for the length, divided by 613,000. Whoops, we weren't writing units for that one. 613,000 millimeters to the fourth. Okay, computing this, the number would be negative 0.00848, and let's check the units using the first term. The 2 millimeters squared on the top cancels with millimeters squared on the bottom, and then we're left with newtons per millimeter squared, which is a megapascal, which cancels with this megapascal over here. So we are left with unitless or radians as expected. So this is our answer. negative 0.00848 radians. Our sanity check would be that the units check out, that the number is small as we would expect for a rotation, and that the number is negative because if working from left to right, we see that, or we expect that the negative torques are going to control over the positive torque, so it's not surprising that the overall angle is negative.